In this lecture, we will proceed to talk about more advanced techniques to solve differential equations. One of these more advanced techniques is called the Laplace Transform. It is widely used in engineering by engineers. So this Laplace Transform is to help you to simplify your calculation in some sense, but it's equivalent to the in solving differential equations by the methods in the previous lecture. Theoretically equivalent, but practically different. Right? Practically, the two methods are totally different, but they give you the same solution. So we will first introduce what is Laplace transform and the basic properties of Laplace transform. Then we use these basic properties to help you solve ordinary differential equations. So these properties are important. It's important to remember what property Laplace transform has. So what is Laplace transform? Laplace transform is just for given function f, you compute a transform of it. It's a different function. So you obtain a function of s. So initially, if you have a function of t, then you apply an integral to the function. Then after integration, you get a function of s. See, for different s, the integral give you different value. Therefore, this is a function of s. Okay? Given s, give you a value. This is a function of s. So it transforms a function of t to a function of s. This is the Laplace transform. Okay, by using an integral from 0 to infinity. So what is the integral from 0 to infinity? It's just the integral from 0 to a given number, while this number tends to infinity. And this is a limit. You have learned the limit, right? So you first compute integral from 0 to a finite number. This is well defined. And then you let this finite number tend to infinity. You get what you get is called the integral from 0 to infinity. So this is your Laplace transform. A given function, the integral give you a function, another function of s. Okay. And what is inverse Laplace transform? According to the name, the inverse Laplace transform of a function of s would be a function of t whose Laplace transform is this function of s. So you want to find a function of t such that its Laplace transform is just this function of s. This is called the inverse Laplace transform. So according to this definition, the inverse Laplace transform will cancel the Laplace transform. They cancel each other. That's why they call the inverse of each other. Okay, so if you apply Laplace transform to this function, you get a function of s because they cancel each other. The inverse Laplace transform cancels the Laplace transform. Okay. And whatever the inverse Laplace transform and Laplace transform, they have both have a same property called the linearity. They are linear transform. So linear transform means that it transforms a sum into a sum of transforms. Okay. You can apply the Laplace transform to each term and then sum up the two terms. This is called linearity. It's linear transform. A linear transform also has another property that you can extract a constant outside the transform. If you apply the Laplace transform to a constant multiple of a function, you can extract this constant outside. So you can directly apply Laplace transform to the function and then multiply this by a constant. So linear transform means that transform sum to sum of transforms, and you can extract a constant outside. Any transform satisfying the two properties are called linear transforms. So Laplace transform is linear, and linear is a very important property which can help you to compute Laplace transform. For example, let's compute the inverse Laplace transform of this given function of S. So here we need to use the property that inverse Laplace transform is linear. So if you are given a complicated function, you can sometimes try to simplify the function into simpler expressions, right? But this function, you can decompose this product into a sum of two simpler functions. And you can verify that if you collect the two terms on the right side, you just look at this function inside the big bracket. The function inside the bracket is this, right? So the denominator is s minus 1 times s. The numerator would be 1. So the numerator would be 1. Exactly the left-hand side. So this verifies that this complicated function is equal to the sum of the two simpler functions. And for each simpler function, you can apply Laplace transform. Okay. So then you sum up the two parts. This is the linear property. Okay. And for simpler function, you are able to calculate inverse Laplace transform either from the basic definition you compute according to the basic definition. You want to find a function whose Laplace transform equals this, but the inverse Laplace transform doesn't have this formula. So to compute the inverse Laplace transform, you need to look at the table. So this is a simpler function, right? This is 1 over s minus 1. This is 1 over s. Okay. You look at the table of Laplace transform, and this is in lecture note. So for which function its Laplace transform is 1 over s, you see it's just the first item. The Laplace transform of 1 is 1 over s. Laplace transform of exponential function is this 1 over s minus a. A is the power here. So exponential power at, this is. So this power, a coefficient in the power become here, the Laplace transform. Okay. So this table is calculated by people based on the basic definition. So people calculated Laplace transform by definition and then summarize their results into this table. You can directly use this table. Okay. So now you see that you want to calculate the inverse Laplace transform of this one. So in the denominator, you have s minus 1. This corresponds to this term. Here, you just choose a to be 1. Then you get s minus 1, right? And this would be exponential t. So what you get is exponential t from there. So you get exponential t here. And the inverse Laplace transform 1 over s is just 1 because inverse Laplace transform of 1 over s is just 1. It's written here. You can directly use it. Okay. So now for each term, it's easy to compute the Laplace transform. Then you sum up the two terms, you get the result. The property that you can sum up the two terms is called the linearity. Okay. So this is a typical application of a basic property, a linear property. Laplace transform and its inverse are both linear. So you can apply transform to each term and then sum up the two parts. Okay, so there are many other results in this table. Okay, whenever you want to compute the inverse Laplace transform, you need to look at this table to see whether the function is already in the table on the right side. Okay, whether you can find the similar function here. If you can find the similar function here, you can directly use the result. Otherwise, you need to simplify your function into simpler functions that appear this column here. So in this question, originally we are given this function, but this function doesn't appear on the table. You cannot find that function here. Okay? It's not on the table, but you can simplify this function into simpler functions that you can find on the table. So for these two simpler functions, you can find it on the table. Okay. So there are many such formulas you can use. So this is a more complicated expression, a more complicated function of S, for which you want to find the inverse Laplace transform. So in order to solve this problem, you really need to simplify this expression into simpler forms. The method is if you are given a rational function. So this is a rational function. Rational function means that polynomial divided by polynomial. If you are given such a polynomial divided by polynomial, then you can decompose it into two parts according to the factor in the denominator. So in the denominator, you have two factors. Okay, according to the two factors, you can decompose the function into such simpler functions. Each function contains only one factor in the denominator. It contains only one factor, and the numerator is always the degree of the polynomial above is always smaller than the degree of the polynomial below. Okay, because originally you have such a polynomial of which the degree is smaller than the denominator. So if originally the degree is smaller than the denominator, after decomposition, the degree is also smaller than the denominator in each term, but you don't know the coefficient. You don't know what is ABC. That's what you want to compute. You want to compute ABC, some constants, such that this decomposition holds. If you can find constants ABC, and then you get such a decomposition. So then you can apply inverse Laplace transform to each simpler part. Okay. So the problem is, what is ABC? You want to find ABC, some three constants. You can, in order to find the value of ABC, you can, on the right side, you can combine the two terms. Then let's compute what's the numerator. The coefficient of S squared appear from two terms. So this is AS, this is S. You get AS squared plus C times S squared. So the coefficient of S squared in total would be A plus C. And then let's look at the coefficient of S. That would be 2A plus B. And then let's look at the constant part, it would be 2B plus C. So you would get such a polynomial in the upper side. And this polynomial on the right-hand side should be equal to the polynomial on the left side. They should be equal. Okay. If they are equal, then A plus C should be equal to 5 because both of them are coefficient of s squared. And 2a plus b should be equal to 3. 2b plus c should be equal to 1. Okay, so the coefficients of s squared and coefficient of s should be equal on both sides. And then you set up the three equations, you can solve ABC. Okay, so you have ABC, 3 unknown variables, and you have three equations. You have 3 equations to solve. Then after solving the 3 equations, you get ABC. Let's see. The first equation minus the third equation give you a minus 2b equals 4. And you also have 2a plus b equals 3. So you have 2a plus b equals 3. So multiply this by 2. You would get 4a plus 2b equals 6. And then you sum up the first 2 equations, you get 5a equals 10. Okay, so a equals 2, right? Then you get a equals 2. If a is 2, then so if a is 2, then c is equal to 5 minus 2. C is 3. So if c is 3, so if a is 2, so b would be 3 minus 2a. So 3 minus 2 times 2 would be minus 1. Okay, so you get ABC, the 3 numbers. When you get ABC, it tells you that the original very complicated expression can be decomposed into these 2 parts, where the first part is as plus b, so it's 2s minus 1. Okay, so let's split it into 2 parts. So minus 1. We write this minus 1 in the second term. And the third term would be c is 3. C divided by s plus 2. So you have these 3 terms, and then you apply the inverse Laplace transform. If you apply the inverse Laplace transform of the original function, it's equivalent to apply the inverse Laplace transform to the 3 terms respectively. Okay, so for the 3 terms, you need to use the table of Laplace transform. So let's look at table. This is s over s squared plus 1. If you look at the table, on the right side, if you have s over s squared plus 1, right? So a should be equal to 1. So you get a cosine a times t. A is 1. So you get cosine t. So this part you would get cosine t. And for the second part, it's just 1 over s squared plus 1. You get sine t actually. And for the third part, you get s plus 2. So s plus 2 means that a should be minus 2. If a is minus 2, you get s plus 2 in the denominator. So a is minus 2, so you get exponential minus 2 times t. Okay, so this is the inverse Laplace transform of this complicated function, because you decompose it into 3 simpler functions, and each simpler function can be found simply on this table of Laplace transform. You can find these simple functions. Okay, so this is how we derive inverse Laplace transform of a very complicated function. We decompose it into simpler functions. Okay. So that's just the simplest property called the linear property. We use the linear property to decompose it into simpler functions and then apply Laplace transform to each term. And there are other properties, more advanced properties. For example, what if you have a coefficient here? If you know the inverse if you know the Laplace transform of sine t, then if you put a coefficient here, you can still calculate the Laplace transform by using this formula. If you have a c here, it's the Laplace transform of this function, f of ct, would be related to the Laplace transform of f in this way. So if you write down Laplace transform of f, and then you change the variable from s to s over c, and then you divide it by c. Okay, so we can illustrate this example here. So you know that the Laplace transform of sine t, if you look at the table, you can simply find that the Laplace transform of sine t is 1 over s squared plus 1. Okay, and then Laplace transform of sine 2t, you get a 2 here. This 2 is this constant. So you should get a 2 here, and then use Laplace transform of sine t. Okay, so you get 1 over 2, and Laplace transform of sine t. But in the end, you should replace your s by s over c. So here is s over 2, which means that you should replace this s by s over 2. In the end, you get s squared plus 4 in the denominator. So here you replace the s by s over 2. Okay, this is the what this means. Okay. Okay. So this is another property. In case that you want to put a constant c in the variable. Okay. So by using this property, you can convert more complicated functions into functions with scaling number here. For example, for cosine square, you cannot find a function cosine square in the table of Laplace transform. Okay, if you look at table of Laplace transform, you have sine, cosine, but you don't have square. You don't have square. So you need to convert this cosine square into some function which appear in the table of Laplace transform. And you can use trigonometric identity here. This trigonometric identity says that cosine square would be equal to half of cosine 2 times t plus 1. So you get a scaling number here. And then for this scaling number, you can use a property that this coefficient 2 comes out into the denominator, becomes 1/4 here. Then you apply Laplace transform to cosine function, then you change the variable to half s. Okay, so then you look at the table. What is the Laplace transform of cosine function? Then you get the answer. Okay. So we always convert complicated functions to simpler functions which appear in the table of Laplace transform. Okay, so Laplace transform can also be used to derivative of a function. Okay, a transform derivative into multiplication by s. So this simplifies differentiation because the derivative is originally more complicated than multiplication, right? But Laplace transform can transform this more complicated concept, differentiation, into multiplication by s. This can help you to solve differential equations. Okay, so this is the formula. It says that Laplace transform derivative into multiplication by s plus initial value times s, plus initial value. Well, it can transform double derivative to multiplication by s squared plus some low order terms involving the initial value at 0. Okay. So let's use this formula to compute Laplace transform of sine cubic. So sine function is cubic if not on the table of Laplace transform. So let's denote this function to be f. Let's call ft to be sine cubic. Then Laplace transform of we want to calculate the Laplace transform of f, which means sine cubic, sine to power 3. But there is no such formula. Okay? But if you look at the derivative of the function, let's first look at derivative of the function. Derivative of sine to power 3 will be 3 times sine squared times cosine squared, cosine t. So this is a chain rule of differentiation. And this sine squared can be furthermore written as cosine squared, 1 minus cosine squared. So you see that you get cosine to power 3. So if you take derivative in sine to power 3, you get cosine to power 3 plus a function cosine t, which you can calculate its Laplace transform. So this term Laplace transform can be calculated because it appears on the table, right? This term doesn't appear on the table, but it gives you some insights, which says that if you take a derivative of sine function to power 3, you get a cosine function to power 3. So because sine function and cosine function are similar, right? This indicates that if you take one more derivative, you get sine function to power 3 again. So let's do it. Let's take one more derivative. If you take one more derivative of cosine t is sine t, negative sine t. Now, a derivative of cosine t to power 3 would be cosine square. And then derivative of cosine would be negative sine. So you get this. Okay, so you get a cosine square, which can be written as the 1 minus sine square. Let me see. So this cancels. Here. You get minus 3 sine to power 3. Well, what's this? This is hold on. This is the original function. This is sine to power 3 is just your f of t. You get the original function, f of t, right? So what do you get? You get, if you take two derivatives, you get the original function multiplied by minus 3. Now you apply Laplace transform. If you apply Laplace transform on both sides, you get a function of s on both sides, right? Okay, but what's this? Laplace transform of double derivative. You can use the formula here. Laplace transform of double derivative is just the original function multiplied by s squared. So it's s squared of the original function, the Laplace transform, minus f0. So what's f0? F0 means that you set 0 in t. So you get a sine 0 is 0. Okay, so derivative of f when t is 0 is also 0. It's something. Something wrong? Yeah, here is there is some mistake here. The number is not correct because when you take a derivative, power 3 comes out. You should get 9 instead of 3. So this is 9. If this is 9, then you get minus 9 here. Let me see. You get 6 sine t minus 9 times f of t. Okay. So you get 6 of sine t minus 9 times f of t. Then you apply Laplace transform, you get the additional terms. You get Laplace transform of sine t, which is s1 over s squared plus 1. Okay. So this should be correct. So on the left side, you get simply s squared multiplying this. Well, on the right side, you get a minus 9 multiplying this. Okay, you can collect the two terms. Let me write. So you can collect the two terms, you get s squared plus 9 on the left side times this. And then you divide the coefficient of Laplace transform of f. You, on both sides, divide this number on both sides. You get your final answer. So this is your final result. Okay. So you see that you introduce a notation f of t to be this function, and then after you taking derivatives, you find a differential equation governing f. You actually find a differential equation, and then you apply Laplace transform. You solve this differential equation actually. Okay, because Laplace transform double derivative into s squared. Therefore, it's simpler to solve this equation of Laplace transform of f without a derivative. Okay, it's simple to solve this equation, to solve this LF, because there is no derivative now. Okay. So this is a very typical question, which shows you an example that you can solve differential equation by using Laplace transform, because this is a differential equation. This is a differential equation of f. F is a function, and its double derivative is related to itself. This is differential equation of f. And you can apply Laplace transform, you find the Laplace transform of f. Okay. If you find the Laplace transform of f, then you take inverse Laplace transform, you immediately get f. So you can solve differential equation in this way by applying an additional inverse Laplace transform. Okay. So there are other properties like if you multiply a function by exponential function, then you apply Laplace transform, then you simply get the original Laplace transform shifted by a number. So you replace your s by s minus a. This is a shift in s. For example, in the table of Laplace transform, you have 1 over f to power 3. You see, in the table of Laplace transform, you have this. You have a constant over f to some power. So if power is 3 means that n is 2. If you choose n to be 2, your power will be s to power 3. So 2 over s to power 3. Its inverse Laplace transform would be t to power square. Okay, so you get what you get is if you consider half of t square, its Laplace transform would be s to power 3, right? And you want to find a function its Laplace transform is a shifted function. So this is simple because you have a formula to use here. Just multiply the function by exponential function. So exponential 2 times t times half t squared. If you consider this function, you multiply it by exponential function. Then its Laplace transform would be the original Laplace transform shifted by 2. So you replace s by s minus 2. Okay, so you see, you find the function, its Laplace transform is this given function. So it means that you find the inverse Laplace transform. Okay, so find the inverse Laplace transform. Okay, so this is the first function. The second function is easier. It's simpler, because you already have the result for the first function. You can convert the second function into the first function in this way. You subtract 2 and then add 2 back. The first term is just s minus 2 squared in the denominator. Second term is s minus 2 cubic in the denominator. So for each term, you should use the same idea. Okay. For example, you know what's the inverse Laplace transform of the second part, right? It's just twice of the first part. Okay. And for this, you should calculate its inverse Laplace transform in a similar way. Okay. I would leave this to you as an exercise after class. So please try to get the answer of this question by yourself. Okay. So work out this problem by yourself. Okay, there is answer here. Okay, so we learned that the Laplace transform derivative to multiplication. It actually also transform multiplication to derivative. For example, if you multiply function by some power of t, then it's equivalent to taking derivative on the Laplace transform side. First taking Laplace transform and then take derivative. This is equivalent to multiplying the function by a power of t before taking Laplace transform. So if you know the Laplace transform of sine t, then you can immediately calculate the Laplace transform of t times sine t. And you can also calculate the Laplace transform of this function divided by t, because this n can be negative number. Okay, if you choose a negative number, okay, and you get a negative derivative. Negative derivative means the integral. Actually, this would be the integral of Laplace transform of sine function. Okay. So this is the answer to this question. So in order to find the Laplace transform of this product function, okay, you use the formula that Laplace transform of this product is just a Laplace transform of f taking a derivative multiplying -1. So this is the formula here. You choose n to be 1, then this is t, then you get a minus derivative. So you get a minus derivative. So capital F would be the Laplace transform of this sine 2t. And if you look at the table, you can immediately find what is this capital F. Okay, so then you take a derivative of this. I'm sure that you can find the derivative of such a function of single variable s. If you find the derivative, you get this. So, and then you should multiply this by -1 to cancel this. So this will cancel. Then in the end, you get your result. Okay. So if you have expert t, then you need to take derivative in the Laplace transform side. Okay. So this is another property of Laplace transform, the last property probably. Okay. And as I mentioned that if you divide the function by t, okay, instead of multiplying by t, okay, so this is multiplying a function by t. This is divide a function by t. If you divide it by t, then you should use this formula because antiderivative is just the integral. Okay, so this capital F would be Laplace transform of the small f. Okay, from the table of Laplace transform, you can find this. Then you integrate it. Okay, you integrate this. You can get arctangent function. Okay, so that's how we find the Laplace transform for various different types of functions. Okay. So in the next half of this lecture, we will use these properties to solve differential equation. Okay. So let's have 10 minutes break, and I will continue to show you how to solve differential equations using Laplace transform. Okay. So one student asked a very good question, that why it's the integral from s to infinity. So it's the integral, but why it's the integral from s to infinity? So this is just a fixed formula. Okay, it's a fixed formula. Okay, anyway, just you only need to use this formula instead of derive it. So let's proceed to the next half of this lecture by solving differential equations using Laplace transform. We have seen one of these examples, a simple example, okay, when we consider the Laplace transform of sine function to power 3. So now let's consider the general problem. If you are given a second order differential equation, how do we solve this equation by using Laplace transform? The idea is just to use this basic formula. So if you have a derivative like this term, if you apply Laplace transform to this derivative, then you get Laplace transform of y times s. So it transforms derivative to s, to multiplication by s. If you consider the double derivative term, its Laplace transform is the Laplace transform of y times s squared. So in any case, the derivative is replaced by multiplication by s. So you would get an equation of this function without a derivative. Okay, so that and what is y0? You have initial condition here, right? So y0 would be this a. So derivative of y0 would be this b. So this will be given by your initial condition. If you have initial condition, you know what is these numbers. Okay. And then you would get if you apply Laplace transform to this, you would get a equation of this function that's denoted by capital Y. You would get an equation of capital Y, which is Laplace transform of small y, that without derivative. Okay, you get this equation, but in this equation there is no derivative except these constant terms. So these are all constants. You replace this by a and b. This is your initial condition, and then you can solve your capital Y as you solve an algebraic equation. Okay, if there is no derivative, it's algebraic equation. After solving algebraic equation, you get a capital Y, and then you take a inverse Laplace transform, you get a small y. So that's the general method for solving differential equation. You first solve capital Y, then apply inverse Laplace transform. You get your small y. This is the a function you want to find in the original question. Okay, let's look at this example. So you want to solve the differential equation governing the forced vibration of a string. Okay, we have seen this equation in previous lectures, that this equation describes a vibration of string under a given force. Then this is the force. Okay. The right hand side is the force. Okay, it's a force acting on the string. Then the string vibrates, and this is the frequency of the string, internal frequency, and this omega is called external frequency. So this omega is the frequency of a force. It's here. It's the frequency of the force. Okay, K is the internal frequency of the string. Okay. And if maybe you have learned in high school that if your frequency of force, of external force, coincides with the internal frequency, then you have resonance would happen. If resonance would happen, then this can destroy this string. Okay, you should have learned this in high school. So, and we will solve this differential equation to let you see why resonance will happen when the two frequencies are the same. So you apply the Laplace transform to this equation. So let's denote capital Y to be the Laplace transform of a small y, and then apply the Laplace transform to the equation. Laplace transform derivative into multiplication by s squared minus some some initial conditions. But here for this example, initial conditions are 0. Since the initial conditions are 0, you simply get multiplication by s squared. Okay. Now you get a k squared. And then you get a Laplace transform of cosine omega t. And what's cosine omega t? What's the Laplace transform of this cosine omega t? You can find this in the table of Laplace transform. So anyway, so Laplace transform of this cosine omega t would be this. Okay, so this is the left side I write here. Okay, so you can solve capital Y. Okay, you can divide this s squared plus k squared to the right side. Then you solve. This is your capital Y. But if you want to apply inverse Laplace transform to this function, then you need to simplify this very complicated expression. It's very complicated. Okay, if k is equal to omega, then you simply get the square here. It cannot be simplified. If you get one factor, only one factor, you cannot simplify it. But if the two factors are different, then you can simplify it. You can decompose it into two terms. Each term contains only one factor. And if you sum up the two terms, you will find that you get a factor that omega squared minus k squared. So you need to divide this factor. Okay. So when k is not equal to omega, you have such a decomposition into simpler functions. Each term is simpler. When k is equal to omega, you simply get a square here, and it cannot be simplified. But these two different expressions have different inverse Laplace transform. If you apply inverse Laplace transform to the first expression, to this case, and this would give you a cosine k times t. So you see that inverse Laplace transform of this is cosine omega t, right? If you replace omega by k, you get cosine kt. You get cosine kt. So this gives you cosine kt. The second term gives you cosine omega t. Okay. And you have cosine kt minus cosine omega t when you take an inverse Laplace transform. Okay. So this is the case when k is not equal to omega. When the internal frequency is not equal to external frequency of force, you get cosine kt minus cosine omega t divided by constant, but every cosine t is a bounded function. The cosine t are always smaller than 1, right? In absolute value, it's smaller than 1. So this is a bounded function. It's periodic function. So this is the position of the vibration string. It shows that the string vibrates in a periodic way. It's described by cosine functions, bounded. Okay. Back and forward. So if k is equal to omega, however, you have a square here, right? In this case, if you look at the table of Laplace transform, the inverse Laplace transform of this contains an extra t. If you contain extra t, it's not a bounded function because when t increase, this amplitude increase. So this is the amplitude of the function. Amplitude increase, and then the string will be destroyed. So this is called resonance. Okay, resonance means the amplitude of vibration increase in time, and then the vibration of string will be destroyed in this case. Okay, so observation is that when the forcing frequency is not equal to internal frequency, you get harmonic oscillation, periodic oscillation, okay, with some magnitude given constant. But if the external forcing frequency is equal to the internal frequency, then the magnitude of the oscillation will be increasing as time increases, and then the amplitude becomes larger and larger as time increases. So this phenomenon is called resonance. Okay, the resonance is a phenomenon in which a vibrating system is driven by external force to oscillate with larger and larger amplitude and without control. So that's the example that Laplace transform is used to solve a second-order differential equation. It can also be solved, applied to solve other more general differential equation, and this is called the differential integral equation because it contains derivative and integral. It contains both, so it's called differential integral equation. The Laplace transform is very flexible in solving such type of equations with constant coefficient. Okay. So why you need the coefficient to be constant? Because if you apply Laplace transform, you want to extract this coefficient outside, right? So it must be constant. If it's a function, you cannot extract function outside Laplace transform. You can only extract constant outside Laplace transform. Okay. So let's consider this differential integral equation. Let's apply Laplace transform. We apply Laplace transform to it. So this term, what do we get? Laplace transform of derivative is equal to Laplace transform of y multiplying s minus y0. But y0 is a given initial condition. It's 1. So if we apply Laplace transform to this term, let's denote capital Y to be this Laplace transform of small y, just to simplify the expression. Then we apply the Laplace transform to the equation. We get s capital Y minus 1 plus 2 times capital Y plus, so this is the integral, right? If you have an integral, Laplace transform of an integral will be Laplace transform of y divided by s, because integral is antiderivative. So let's simply write down the integral here. So Laplace transform of t would be 1 over s squared. Okay. Okay, so it remains to calculate this term, Laplace transform of the integral. So let's look at this term. So this is simply 1 over s. So you see that if you consider the derivative, it becomes multiplication with s. If you consider integral, it would become a multiplication with 1 over s. Okay. So you would get 1 over s here. Then you collect all the coefficients of y, which consists of s, 2, and 1 over s. So 3 terms. These 3 terms multiply in capital Y. Okay. So the initial condition is 1, I think. Yeah. Initial condition is 1. So you move this to the right side and divide both sides by this coefficient. You would get an expression of this capital Y. After you get this expression, you can apply inverse Laplace transform. You get inverse Laplace transform, you get a solution Y. But when apply inverse Laplace transform, you meet this 1 over s. So recall that if you have 1 over s, it means that you are computing an integral, because Laplace transform of an integral would be Laplace transform of the function divided by s. Okay. Now you have s in the numerator. It means that you should take a derivative, because Laplace transform of a derivative is equal to the Laplace transform of this function multiplying s. Okay, because Laplace transform of this function is s1 over this is 1 over s plus 1 square. So let's look at this term. So we know that Laplace transform of t is 1 over s squared. Then Laplace transform of t times exponential t is this function when you replace s by s minus 1. Here we want this to be minus t. So s minus 1 would be s plus 1. Okay, if you multiply function by exponential function, then it's equivalent to make a change of variable, just shift it by this number, by minus 1. So you replace s by s minus 1, so get this. Okay, so but you still miss this s. So if you take a derivative, Laplace transform of a derivative would be Laplace transform of this function multiplying s minus this function initial condition. Okay, so the initial condition is 0 actually, because when t is 0, you get 0 times exponential 0. So this would be 0. Okay. So this is how you get this term. You see, finally you get Laplace transform of this is this. So inverse Laplace transform of this is just this function. So that's why you have this function here. Okay. So this is similar. You have an integral instead of derivative because you divide s instead of multiplying s. Okay. So this is a typical type of question for differential integral equation. So for differential integral equation, you also need initial condition. So how many initial conditions you need depend on how many derivatives you have. If you have only one derivative, first order derivative, you only need one initial condition. Okay. If you have a second order derivative, you need two initial conditions. It completely depends on how many derivatives you have, what's the order of derivative. Okay. So that's the second example about solving differential integral equation. In addition to this, you can also solve more complicated system of equation. So system of equation means two equations coupled together. They need to be solved simultaneously in a coupled way. Okay, so the idea is similar. You apply Laplace transform to both equations. Then you get equation of capital Y1, equation of capital Y2, okay? And use the initial condition. So for example, let's look at the first equation. If you apply the Laplace transform to the first equation, you get a Y, capital Y1 is the Laplace transform of small y1. So you get this. Okay. Then this is 1. So you get S here. Let's collect all the coefficients of y1. You get S minus 1 times y1 minus y2 equals 2. Okay, so this is 1, this is 1. You get 2 on the right side. Okay, so you get an equation relating y1 and y2. Okay, so you would get an equation relating y1 and y2. This is S minus 1, this is minus 1. Okay, S minus 1 minus 1, it's the same. So if you apply Laplace transform for the second equation, you would also obtain an equation relating y1 and y2. Okay, similarly. So anyway, you will so Laplace transform of 1 is not 1. Laplace transform of 1 is 1 over s. Okay, so this is not 2. This is 1 over s plus 1. Okay. Then that's why you have 1 over s plus 1. Okay. So anyway, this is not important. The important thing is that if you apply Laplace transform, you get an algebraic equation. You get a linear equation of y1 and y2 without derivative. So this time you don't need to solve differential equation. You need to solve a linear equation without derivative. So two unknown number, two equations. And everyone can solve such equation from primary school or high school. So anyway, you need to solve two numbers from two equations without any derivative. Okay, so then if you get the two numbers with some expressions of s, then you can apply inverse Laplace transform. When you apply inverse Laplace transform, you apply it to every term. Okay, so for example, the first term would give you exponential 2 times t. This is written in the table directly. The second term, you can first collect this. So divided by s means that you would get an integral in the inverse Laplace transform. So if you have 1 over s, you would get an integral. Okay, then this term appear directly in the table. So it is t actually. So inverse Laplace transform of 1 over s squared is t. Or you can say Laplace transform of t is inverse is 1 over s squared. But this is not 1 over s, but it's s minus 2 here. So you need to multiply this by exponential 2t. If you multiply it by exponential 2t, you would get a shift in the variable s. So you get t times exponential 2t for this part. But then you need to compute the integral from 0 to t. Okay, so when you compute the integral, you need to change the notation. You cannot use the same notation in the function and the integral. Okay, you need to use different notation. So that's why I change the notation to tau, just a change the notation. Okay, so since you have 1 over s, you need to compute the integral. If you have 1 over s squared, you need to compute 2 integrals. Okay. Okay, so then you can get y1, you get y2, just apply inverse Laplace transform and use the property of inverse Laplace transform. So the property includes that if you have 1 over s, you have an integral in the inverse Laplace transform. If you have 1 over s squared, you have a double integral. Okay, so that's all for today. Okay, so we have learned several different topics. First, we learned the concept of Laplace transform and its inverse. Okay, you can find Laplace transform and its inverse by using the table of Laplace transform. Don't calculate it by hand by using basic definition. Don't use basic definition. You should use table of Laplace transform. Okay. You always use this table. If your function is not on the table, you should try to convert it into simpler functions that you can find it on the table. Okay, so this is the first part, Laplace transform. Then we introduce how to apply Laplace transform to solve differential equation with constant coefficients and the differential integral equations and system of equations. Okay, this is the second part.